So now let's look at reaction rates. Rate is just change over time. Okay, so your speed, your miles per hour, you've got a change in distance over time. Anything that is changing something over time is a rate. So we're changing usually the molarity or the concentration per time. So molarity per time, molarity over the time unit, and it's often seconds, is your unit for is your unit for rate, concentration over time. There's your concentration brackets, change in concentration over change in time. So if we look at this chemical equation, we can see that nitrogen and hydrogen are both reactants, so their concentrations would decrease over time. Nitrogen decreases at only 1/3 the rate that hydrogen does because of the stoichiometry. Okay? And then ammonia, we would expect to start down here. In the beginning, there is no ammonia, and it will increase. Well, it will increase at twice the rate that nitrogen decreases. So we should be able to look at a graph comparing rates. So if you were to look at these three lines without being labeled, you should know that these two, the red and the black, are reactants. You can see that the nitrogen is going to decrease at a slower rate than the hydrogen because of the stoichiometry, and that the ammonia would be the only one that's a product and is increasing. And if they had another one or asked you to draw it, you should draw it at about twice the rate or 2/3 the rate of hydrogen, but 2/3 is a little more difficult to do. So you can compare rates. Okay? Forward rates will always decrease over time because your concentration of reactants is decreasing. So there's fewer collisions, so collision frequency goes down and rate goes down. Your products are formed at a faster rate until they reach equilibrium because their concentrations are increasing. So many of the reactions in chemistry are reversible. So early on, the rate is determined only by the reactants. So for us, only reactants will be present in the rate laws. We're not going to include reversible reactions. That is much more involved kinetics. So when you're looking at rate laws, they will only include the reactants. The rate law itself, okay. So if this was a reversible reaction, eventually C and D would go back to form A and B, and it would go back to form C and D. But we do not deal with the products of reversible reactions in first-year kinetics. So that is the typical rate expression or rate law expression. Rate is equal to K, the rate constant, a lowercase k, which is determined by the reaction and the reactants themselves. And then this is the order of the reaction. And that is determined experimentally. So K is the rate constant and N is the order of the reactant, whatever reactant that you're putting in your rate law. And it's usually a positive integer. It can be a negative and it can be 1/2 orders, but I would expect you're going to see 0, 1, 2, 3 order reactions, and it must be determined experimentally. You can compare rates. You can say the rate of NO is formed at twice the rate of O2, and NO2 disappears at the same rate of NO, but you can't get a rate law from a balanced equation. You can only compare rates, and that's something that students always get confused. A rate law is different from just comparing a rate. So the concentration of the products, we said, do not appear. We must determine them experimentally. We cannot get it from a balanced equation. So a first order rate law means that you have a reaction. that when your concentration doubles, your rate also doubles. So they are related to each other by the first power. You could also have a concentration tripling and the rate tripling, or doubling and doubling, or even if it was cut in half and cut in half. If you have a relationship between your rate and your concentration that does the same thing, you're going to have a first order reaction. These are exponential relationships. So a second order means a square effect. So this means if A, your concentration doubles, so you double your molarity from 3 to 6, and if your rate quadruples, that's a second order, a much greater effect on your rate. Notice the slope of your line is much steeper with rate and concentration. Okay? So first order, concentration doubles, rate doubles, or concentration triples, rate triples. Second order, A doubles, rate quadruples. Or you could even have concentration tripling and changing your rate 9 times. That's still going to be a square effect. Third order is concentration doubles and you have a cubic effect. The rate increases 8-fold. So if you have a substance that's third order, it has a huge effect on the rate. So it is going to definitely be one of the larger factors in that rate, what you do with that third order reactant. So again, if you had a reaction where you tripled A, you would actually cube that. It's a cube exponential factor. You'd have a rate 27 times as great. And then there can be square root orders and -1 orders, but for the most part they're very rare, and you would be able to figure them out mathematically or even by observing a graph. So whenever you see that you have a negative effect, you've got to think of that as being a square root order or a -1 order. So if you have a 0 order, the concentration has no effect on the rate. So you double it, triple it, rate doesn't change. First order, concentration doubles, rate doubles. Second order, concentration doubles, rate quadruples. Third order, concentration doubles, rate increases 8-fold. These are usually very easy to predict. Okay? So we've got our 0, first, second, third orders are the most common that you'll see on the AP exam. So your method of initial rates has you run an experiment several times, take initial concentrations and then vary them, and you want to make sure that you measure your rate just after the reactants are mixed. That's why it's called the initial rate, so that you don't get the reverse reaction kicking in and giving you complications. So that's why it's called method of initial rates. The change in rate happens pretty quickly after you add the reactants. So this was the example that's in your book. So you've got 3 reactants here, and you would be trying to find out these exponents, N, M, P, whatever you want to call them. If you do have more than one, you're going to find them one at a time. You can call them all N or X or Y or Z. It really doesn't matter. So you're going to use experimental data to determine those. So you'll be given data, and you'll pick out a set of data that allows you to see how the change in the bromate ion affects the rate. So you do need to review your kinetics so you know what numbers you're looking at. So you need to find a set of data where bromate changes and the other substances are held constant. so that you know they're not affecting the rate, and then you see how the rate is affected. So the setup of that is usually you don't have to write rate 2 and 1. You want to put your largest rate over your smallest just to make sure you get a whole number. It's just easier to deal with. So when you divide those two rates, so here was your data that you picked and there are your rates. Then on the other side, you have these two substances are going to cross out because they were held constant. So now you have the change in rate, the rate doubled when the concentration doubled. So 2 is equal to 2 raised to what power? And of course, that's the first power. So that is order 1, and you are first order with respect to bromate. The second reactant is the bromide ion. So it doubles there, and you pick that change in rate, and those were held constant. So they can't be affecting that change. So the rate doubled, and the concentration doubled, and that is also first order. Often you can see that the rate doubles and the concentration doubles. It's always safer to just quickly write that out. And you honestly, probably on the exam, don't need to write those numbers down that are held constant. You can maybe just cross them off or indicate that they were held constant. It's probably safer to put them in and cross them out, but you often can just make a statement, qualitative, but you just have to look at what they ask you. If they ask you to calculate or support, then that's better with a calculation than just an explanation. And now we move to the hydrogen, and sometimes you have to look around a little bit. So there's where hydrogen doubles, but those stay the same. So you need to find where hydrogen changes and those stay the same. This time, however, you notice that the rate does more than doubling when you double the concentration. The rate quadruples. So now you're saying 4 is equal to 2 raised to what power? Well, that's the square of 2, or second order. So hydrogen is second order. Your rate law expression then becomes this. Now they're going to want you to find K. So you go back to your first set of data. That's typically what we use unless they ask you to use another experiment. So read carefully. So take your first set of data with those molarities and that rate and put them in. So if rate is equal to K times your concentrations raised to their power, then manipulating for K gives you this. And your K can usually be found with any set of data as long as you realize there may be some experimental error. So your unit of K will be important in kinetics. So your unit of K will depend on the order of your reaction. So you're always going to have rate, which is always molarity over time. So molarity time -1, divided by some molarities down here. So if you're first order, then this molarity cancels with that, and you end up with the unit of just inverse time. For second order, so you would have molarity squared down here. One of your molarities cancels this one out, leaving you with molarity -1 time -1. So second order takes off one of your molarities and of course flips it on the bottom. So that's molarity -1 time -1. And then for third order overall, okay, you're going to be left with molarity -2 and time -1. So memorize your rate constants. Usually they're going to ask for them, and memorizing them is the fastest way. I'd put them on your cheat sheet so that you're not having to worry about them. If you have, go back here, if you had zero order, so if you have zero order, then your rate is going to be equal to K. So then you've got molarity over time. So method of initial rate. So I've done several example problems for you. You should stop and work all of them yourself to remember what you're doing. So I've only got one reactant here. So there's my change in concentration. Again, always putting for me the larger number over the smaller. There's my rate. It doesn't matter if you put the rate on this side or this side, but it does matter that you know you're raising the molarity to that power. So just make sure that you are setting them equal, but that you know you're not going to say 4 to the nth is equal to 2. Then you're really going to mess yourself up. So the rate quadrupled and the molarity doubled. So what's the relationship of the rate to the molarity? It's the second order. So that should help you make sure that you know you're putting that exponent on the molarity. So there's your rate law for that. And your K would simply be take that first set of data and put your molarity for that first set of data. And don't forget to put it into the rate law, so you need to square it, and that gives you your K. Your units, again, would be, since it's second order overall, molarity -1, time -1. I'll let you go through this one yourself. Okay? In fact, you can stop the slide and cover the bottom up and see if you can get the first order for carbon monoxide, the first order for nitrogen dioxide, and the rate law. They're often messy problems, so you need to make sure when you're doing this that you're keeping your concentrations matched with your rate. So here's your larger rate number. So there's your set of data for carbon monoxide. So there's that rate and that rate. And then once you've written those down, you carefully can go across and put your concentrations in correctly. So again, just to make sure, I've seen a lot of good students, if they don't give you user-friendly numbers, just make a mess because they're not looking across or they're making mistakes. Here, you've got these sets of data to use for NO2. And your K, if you work it out yourself, should come out to 0.19, molarity -1, time -1. Notice this would be second order overall. So that leads you to that rate law units, or rate constant units, excuse me. So this is a nice, easy one. Remember, you don't have any multiple choice on your exam, so if you do get a kinetics, you are going to have to explain it. But it's very easy to see where A changes and B and C were held constant. They gave you nice, easy numbers with your molarities, so you really should be able to come up with first order, second order, first order. So please work through this one and use this as an example problem to make sure you're doing it correctly. I did not work it out for you. I did work the K out for you. So if you don't come up with this rate law, let me know. But if you do, you should get this K value. And since this is fourth order overall, it would be molarity -3, time -1. We don't know what the time unit is, so you can use any time unit there you want. And then this one I worked out for you, but I did not show the work for K. So you should be able to stop and go through this one. This has pretty nice user-friendly numbers. So you've got second order there. And this last one has zero order, so I do want to talk about zero order. So if we look at A, we can see that we're going to use this set of data right here where B doesn't change. And if we glance over, we see that our rate does not change either. So if it looks like they're asking you to explain it, you could say concentration doubled and rate stayed the same while B was held constant. You need to mention B was held constant. Therefore, it is zero order, meaning changing A had no effect on rate. To solve it mathematically, though, which is just as safe, you get a 1 is equal to 2 to the nth, and of course, anything raised to the 0 power is 1, so that's how you prove that first order. And then B ends up being a nice first order as well. Or excuse me, this ends up being 0 order, and B ends up being first order. And then you can work through and get your K. So if you can do these problems, you're in pretty good shape. There are a few that we'll do later on as we review these kinetics. We haven't started doing our kinetics FRQs where you have something not held constant, and we'll have to review that.